These are the frequently asked questions for pre-calculus for section 5.2, day 1. And I'm going to start with number 1. It says, prove the algebraic identity by starting with the left-hand side expression and supplying a sequence of equivalent expressions that ends with the right-hand side expression. So we're using algebra to get us used to what we're going to have to do to prove our trig identities. We have x cubed minus x squared all over x minus x minus 1 times x plus 1, and that is supposed to, in the end, equal 1 minus x. Now, there are a couple of different ways to do this, and the first thing that I noticed was that we could go ahead and divide out the x. Now, if you didn't notice that, then this probably got a little more difficult for you. So, perhaps I will go ahead and do that as if you didn't notice that piece. So we'd have x cubed minus x squared over x, which, like I said, would be easiest if you just went ahead and factored out an x. But if you don't notice that, then you're going to go ahead and do the FOIL on x minus 1 times x plus 1, which is a sum and difference pattern. And then we'd go ahead and I would change it to adding addition, because truly the most missed case for any test or any assignment is that somebody misses a negative. So I change it to adding a negative x squared plus 1 and distributing that. And then go ahead and slap a 1 underneath there, because we know that if we have fractions, we're going to need a common denominator. And this one will need to be multiplied by x on the top and the bottom. And we'll have x cubed minus x squared over x plus negative x cubed plus x all over x. Now that they have a common denominator, we can go ahead and combine like terms. And we will see here that we will have x cubed minus x cubed, which will be gone. We will have a negative x squared plus x over x. Now, I remember that this seemed kind of backwards. It was 1 minus x. So I'm going to go ahead and change around my negative x squared plus x and make it x minus x squared over x. Then I'm going to factor an x out of my numerator. And then I can cancel, because remember, canceling is a form of division. So we have to see multiplication in order for us to divide that out. And this will give us what we needed to get, which is 1 minus x. So like I said, this problem would have been a little easier if you had noticed that you could cancel out an x for the very first fraction up here, because then that immediately becomes x squared minus x plus whatever we have behind it back there. But for most people, the reason that you had trouble with this one is because you didn't notice that. So that's the reason that I did the problem the way that I did. Number 15 is the next one here, and isn't that pretty? Number 15 says 1 minus cosine u times the quantity 1 plus cosine u over cosine squared u, believe it or not, equals tangent squared u. Well, it does. So the first thing that I'm thinking here is, they've got a lot going on in that numerator. So maybe I better go ahead and multiply those two together and see what happens. And that is a sum and difference pattern. So we get 1 minus cosine squared u over cosine squared u. And hopefully you notice, hey, wait a minute, 1 minus cosine squared u, well, if I take cosine squared u plus sine squared u equals 1, which is one of our Pythagorean identities, and I subtract cosine squared u from both sides, that'll give me sine squared u. And sine squared u over cosine squared u is tangent squared u. So that one was all about simplifying the numerator by just multiplying. Whether or not you had to FOIL it or you remembered the pattern, it doesn't make any difference, as long as you can get that to the 1 minus cosine squared u and realize that that is a tweak on our Pythagorean identity. Number 18 is another kind of interesting little problem there. So with number 18, we're going to take secant squared theta minus 1 over sine of theta, and we are going to get sine of theta over 1 minus sine squared theta. All right, so first thing I thought was secant squared theta minus 1. That comes from one of our Pythagorean identities, and that is actually tangent squared theta. And then I thought, you know what, I'm going to go ahead and change that tangent squared theta into sine and cosine so I can see what's going on with this. Because often when we change things into sine and cosine, it just brings it into view for us, what we have to do. And I see I have a fraction divided by a fraction, which means that I have to multiply by the reciprocal. So I will have sine squared theta over cosine squared theta times, well, if I'm supposed to divide by the sine of theta, that will be 1 over the sine of theta. And of course, one of those sines of theta is going to cancel out. So now we have sine of theta over cosine squared theta. Now, keep your eye on the prize. That is what we wanted. We are almost there. We have the sine of theta in the numerator. I need to get 1 minus sine squared theta in the denominator, and that is a use of the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. If we subtract sine squared theta from both sides, we can use that 1 minus sine squared theta to substitute in for cosine squared theta. So this will be, indeed, sine theta over 1 minus sine squared theta. And we have what we were supposed to get on the other side. So this one was about being able to recognize that when you look at the answer, what we're supposed to get, the result there is sine of theta over 1 minus sine squared theta. It does not involve tangent. And one of the easy ways to work with tangent is to change it into the sine of theta over the cosine of theta. And then you'll be able to see what's going to happen. Next one up is the lovely number 25. Number 25, we have cosine of beta over 1 plus the sine of beta. And that is supposed to equal 1 minus the sine of beta over the cosine of beta. So we'll start here on the left-hand side. And what I start thinking is, you know what? I need that 1 minus sine of beta on the numerator of the other one. And that's a really good conjugate for what I have anyway. So why not just go ahead and try it right away and see what happens. So in the denominator, we have that difference of two squares pattern again. So that will be 1 minus sine squared beta. And in my numerator, I have cosine of beta times the quantity 1 minus the sine of beta. Now, I look at the denominator and I notice, wait a minute, that is cosine squared beta. Because again, that's using our cosine squared beta plus sine squared beta equals 1, our basic Pythagorean identity here. And we'll have the cosine of beta and 1 minus the sine of beta on the top. And the last thing I need to do is cancel out one of these cosines of beta. And what I have left is 1 minus the sine of beta over cosine of beta, which is exactly what I wanted. So again, keep your eye on what you're supposed to be getting at the end and think, how can I make that happen? What could I do to this that will get? Notice my first step was, how am I going to get a 1 minus sine of beta in the numerator over there? And that was just by multiplying. And then things fell into place. Next one up is number 30. Tangent squared theta minus sine squared theta equals tangent squared theta times sine squared theta. All right, so start with this side. And think about where to go. I mean, pretty obviously, I still need tangent squared theta and sine squared theta in this. So I try to figure out how I'm going to make that work. Well, what I'm going to do is I'm going to change this into sine and cosine to see what happens. So sine squared theta over cosine squared theta minus sine squared theta over 1. And now I'm going to go ahead and put those two fractions together by getting myself a common denominator, which in this case is cosine squared theta. So let's see what we have. We will have sine squared theta over cosine squared theta minus sine squared theta cosine squared theta over cosine squared theta, which means we can go ahead and put those two together. They do have a common denominator now. So that will be sine squared theta minus sine squared theta cosine squared theta all over cosine squared theta. Now I notice that I could factor a sine out of my numerator up there. In fact, I can factor a sine squared theta out of that. So now I start thinking, what I want here is to have tangent squared theta and sine squared theta. Well, I have tangent squared theta right here. It's sine squared theta over cosine squared theta. And what I have left is 1 minus cosine squared theta. So I'm more than halfway there, because now I just need to figure out how do I get the other part of this, which is sine squared theta, and that's just the Pythagorean identity right here. That is sine squared theta. So we have sine squared theta over cosine squared theta times sine squared theta over 1. And now this is tangent squared theta, and anybody can see that who knows anything about trig, sine over cosine, tangent squared theta. And this is sine squared theta. And we have it. And in fact, you really wouldn't even need a fraction here, in this part, but it does make it easier for some people to follow, because when you have fractions, it really is easy to work with all fractions as you go through it. But there we have it, tangent squared theta times sine squared theta. Now number 35. Number 35 says we have the tangent of x over the secant of x minus 1. And keeping my eye on the prize, I see that. And that really tells me that I want to use the conjugate here, because I want to get a secant of x plus 1. So I'm going to multiply by the secant of x plus 1 to the numerator and the denominator. Again, we're really just multiplying by 1 here, because the secant of x plus 1 divided by the secant of x plus 1 is just 1. So we're manipulating. We are not changing its value. And in the numerator, we'll have the tangent of x times the secant of x plus 1 over secant squared x minus 1. Now, I need a tangent in my denominator, and I've got one, because that's another one of our Pythagorean identities down there. We've got secant squared x minus 1, and we know that that equals tangent squared x. And now things are falling into place, because I see that I have a tangent in my numerator and my denominator that can be canceled out. And that leaves me with the secant of x plus 1 all over the tangent of x. And that is exactly what I wanted to get on the other side of that equality. Next up, we have 37. 37 is, it's kind of a monster here. We have sine of x minus cosine of x, and we want that to be the sine of x plus the cosine of x. Now, there are a couple things here that indicate to me that I'm going to have to do some FOILing, and those things would be the 2's. The 2's really tell me, okay, I'm going to have a sum of squares. I'm going to have to square it. That's how I'm going to get the 2's. You can think back to the formula, the quantity a plus b squared equals a squared plus 2ab plus b squared. If I'm going to get the 2's, that's going to be the easiest way to do it. Which means, in this case, I'm not going after the conjugate of the denominator. I'm trying to get that binomial squared pattern. So this will do it. my denominator now is going to be the sine of x times the sine of x plus cosine of x times the sine of x plus the cosine of x, which is really squaring it. So if we do FOIL, we'll get sine squared x plus 2, oh, maybe we should put the cosine first. Nope, they had it sine and then cosine. So I'm going back and I'm looking at what do they have, you know, what is their order. So sine of x, cosine of x, and then we have plus cosine squared x. My numerator happens to be a sum and difference pattern, so you could do FOIL, but you don't really need to do outside times outside and inside times inside because they're conjugates. It's going to drop out. So we will get sine squared x minus cosine squared x. All right, now I'm seeing my 2 in my denominator, which is great, but I also notice that I don't need these two here. And because sine squared x plus cosine squared x is 1, I can rewrite that, and I can say, woohoo, I'm done with the denominator, and just focus on the numerator. So the numerator, I need 2 sine squared x minus 1. Well, there's no cosine in the right side. So what I'm going to have to do is take sine squared x and subtract 1 minus sine squared x using the Pythagorean identity. And then I would go ahead and distribute the negative sign. And take a look at what I have. Well, I have sine squared x minus 1, but then I have plus another sine squared x, which is 2 sine squared x minus 1 over 1 plus 2 sine of x cosine of x, which is what I needed. So that's a big phew on that one. You know, that takes a lot of work. But the first step is recognizing that if we want a 2 to show up, we're going to have to use a binomial squared method to make that happen. And last but not least, we have the lovely 40. There's a lot going on in this problem. So we have the sine of A cosine of B plus the cosine of A sine of B over cosine of A cosine of B minus sine of A sine of B. And you look at the right side, and everything is tangent. Absolutely everything is tangent. So I think, well, how could I make tangent show up out of all of this? And I realized I need sine over cosine. So I'm looking at what I have here and thinking, I need to divide that by cosine. That I need to divide by cosine to get it out of there. This I need to divide by cosine to get it out of there, but there I could divide by cosine to get tangent. So what I really need to do is I need to multiply my numerator by 1 over the cosine of A cosine of B. If I do that, that will get rid of these two terms, and it will give me tangents in the other two positions. But what I do to the top, I have to do to the bottom. And boy, oh boy, does that look weird. But that's what we need to do. We need to multiply both the numerator and the denominator by 1 over the cosine of A, cosine of B. All right, well, let's go. So we will have the sine of A, cosine of B, over cosine of A, cosine of B, plus cosine of A, sine of B, over cosine of A, and cosine of B. And that's just the numerator. So the denominator will now be cosine of A, cosine of B, over cosine of A, cosine of B, minus sine of A, sine of B, over cosine of A, pardon me, cosine of B. And now we go back and see what's going to cancel out and what we have left in all of this massive confusion. So cosine of B is gone. Cosine of A is gone. Cosine of A and cosine of B is gone, leaving us with a nice little 1 right here. And then we have sine over cosine and sine over cosine, which of course would be tangent again. So on the top, there is tangent of A plus tangent of B over, we have a 1, minus tangent of A, tangent of B. And there it is.